In this video, we are going to do an example checking to see if something is a vector space. And before we do that example, we will look at something that we already know is a vector space, the familiar vector space C2. Remember that a vector space is four things: a set V of vectors, it doesn't have to be called V, but generally we call it V, a set of scalars, a definition of vector addition, and a definition of scalar multiplication, how to multiply a scalar and a vector together. If these four things satisfy the 10 vector space axioms, then those four things together are a vector space, and we would say in this case that V is a vector space over F. In the familiar vector space C2, the definition of a vector addition is simply to add the entries of each column vector component-wise. So the vector xy plus the vector wz is simply the vector whose components are x plus w and y plus z. And the definition of scalar multiplication is to simply multiply the scalar by each complex number entry in the vector. It turns out that the zero vector in C2 is simply the vector whose entries are zeros, and the additive inverse of the vector xy is the vector whose entries are the additive inverses, or the opposites, we could say, of the entries in the vector. These two things may seem obvious, which is maybe good, but it can also work against us if we assume that the zero vector and the additive inverse are going to be the same in every vector space. So let's do an example, and we're going to essentially take C2 and just make one change to it. So we have the same set of vectors, so we've got column vectors where each entry is in C, a complex number. The field will still be C. We'll keep the same definition of scalar multiplication. The only thing that we're going to change is the definition of vector addition. And instead of adding components, we're going to subtract x minus w and then add a 2. Just an arbitrary, I just chose that arbitrarily for this example. And the second component is going to be the difference of the entries in each vector, also plus 2. Now, let's check and see if this is a vector space. In other words, if these four things, these two sets together with these definitions, satisfy the 10 vector space axioms, then this set V is a vector space over C. It's not C2 because it's got a different definition of addition. We could give it a name if we wanted, but it is a vector space. And if any of those 10 vector space axioms are not satisfied, even if 9 out of 10 are satisfied, if one is not satisfied, one or more, then V is not a vector space over C. All right, well, in particular, let's look and see what the zero vector would be. Remember, the zero axiom says that if U is a vector in V, U plus the zero vector has to be equal to U for every vector in V. So for all U in V, we would say. And then the additive inverse says that U plus the additive inverse of U, sometimes we say the opposite of U for short, has to be equal to the zero vector. Notice that the additive inverse refers to the zero vector. So we have to know what the zero vector is before we can check the additive inverse axiom. It's a common mistake to assume that we know what the zero vector is and check the additive inverse axiom based on that assumption. But we cannot assume anything. We can't assume that we know what the zero vector is, or even if the zero vector exists. In other words, this axiom is the definition of the zero vector. It is the unique vector that satisfies this equation. The fact that the zero vector is unique is a theorem that we can prove. It's true in any vector space, so I'm not going to elaborate on that for now. So to check the zero axiom means essentially to see if we can find a vector that satisfies this axiom. And then that vector also is the zero vector, and we can use that in turn to check the additive inverse axiom. Well, how do we check this? We're just going to plug in some vectors here. So u is just an arbitrary vector. Let's call it, so we'll say check 0. So we'll just use xy here. Notice u is an arbitrary vector in the vector space. The zero axiom can be written like this regardless of what the vector space is, regardless of what the definition of a vector is. The definition of a vector comes from the definition of the set V. So now to check it in this particular example, I'm going to use a vector, a specific vector, or a vector specifically from this vector space V. In other words, a column vector with two complex number entries. I could use any letters that I want here. I could do, x1, x2 as we commonly do. But if it's just a C2 with two different numbers, we'll just use different letters to keep it simple. And the zero axiom says if I add this vector plus the zero vector, well, I've got to get xy. But what is the zero vector? Well, it's going to have to be a vector in V, but I don't know what it is, and I can't assume that it's the vector with two zeros in it. I can't assume that this is the case. So I have to put something else, some arbitrary number there, or arbitrary entries. So let's just say, Z1 and Z2 for the two entries of the zero vector, and that has to equal the original vector xy. Okay, so now what do we do? Well, we use the definition of vector addition right here. Okay, we are also going to use the definition of vector equality for column vectors right here, which I should mention we are assuming is the same as in C2. In other words, we could just say, come up here and we could say two vectors are equal if their entries are equal, in other words. If I say two vectors are equal, that means that the entries are equal to each other. Okay, so we're going to use the definition of addition and the definition of equality to check and see if this is true, and in particular, if we can solve this equation. We want to solve for Z1 and Z2. If we can find complex numbers that we can put in for Z1 and Z2 that make this true, well, then the zero axiom is satisfied and we have found the zero vector. All right, so here's our definition of vector addition, and I'm just going to do this to it. So I'm going to do x minus z1 and add a 2. And y minus z2. And the right-hand side stays the same. All right, so we used the definition of addition. And now we'll use the definition of equality. Notice that inside the brackets here, this subtraction and addition, that's subtraction of complex numbers and addition of complex numbers. In other words, we use the definitions of, in this case, addition and subtraction from the field of complex numbers in particular. So this is the normal definitions of addition and subtraction for numbers. And now we use the definition of equality of vectors that we reviewed up here. So we basically just set each of the entries, corresponding entries, equal to each other. So this entry has to equal this one has to equal this one. So the first entries have to be equal, and so do the second entries. And now this is no longer an equation about vectors. This is just an equation about complex numbers. So we can solve this equation the way we would normally solve an algebraic equation. You could subtract x from both sides from the first equation, subtract y from both sides of the second equation, add z1 to both sides of the first, and add z2 to both sides of the second. You could probably Do that in your head. And we can see that apparently Z1 and Z2 are both equal to 2. You could see that if you just plug a 2 in for each of those. Minus 2 plus 2, just, those cancel, and you're just left with x and y. So apparently the 0 vector, if we write it as a bold numeral 0, is equal to the vector 2, 2. That's the 0 vector in this proposed vector space. More specifically, the 0 axiom is indeed satisfied, and this is the vector that satisfies it. Now, that doesn't prove that this is a vector space. That's 1 out of 10. We have 9 more to check. But there's the 0 vector, and in particular, it's not 0, 0. This might seem strange or wrong, but there's nothing wrong with it. It satisfies the definition of 0. It satisfies, which is the same as the 0 axiom. So now that we know what the 0 vector is, we can check the additive inverse. I'll just say AI for short. And again, I cannot assume what the opposite of a vector is. I can't assume that the additive inverse of xy is the vector whose entries are minus x and minus y. Maybe it is, maybe it isn't. Maybe the additive inverse doesn't even exist. Maybe this is not satisfied. But I do know what the 0 vector is now. It's not 0, 0, it's 2, 2, as crazy as that seems. Okay. So we'll write down the additive inverse axiom. Notice I've chosen xy again as an arbitrary vector. And the additive inverse of that is this is a symbol. So you might think this is -1 times this vector. That's not what this means. This symbol means simply the additive inverse, and in particular, it means the unique vector. That's another theorem that the additive inverse of every vector is unique. It's the unique vector that satisfies this equation. So when you take a vector and add it together with its additive inverse, you always get the 0 vector. So let's see if we can figure out what the entries of the additive inverse are. Well, let's make it a little simpler, and I'll just write WZ for the entries of the additive inverse. So this is a vector in V, and it's a column vector with 2 complex number entries in it. I'm going to write it as an arbitrary vector with, doesn't matter what letters I use as long as they're different than the letters that I use over here. Okay, and now we'll do the same thing. We're going to use the definition of addition and the definition of equality and see if we can solve for W and Z. Okay, so we've done this once before, so we can do it maybe a little quicker. So here's using the definition of addition from up here. Okay, and now we get a system of equations. We can, subtract 2 from both sides. We get this result where W is just the same as X and Z is the same as Y. In other words, the additive inverse of every vector is itself. So that's unusual, unexpected perhaps. Okay, so the additive inverse axiom is indeed satisfied. And the vector that satisfies it is xy. In other words, every vector is its own additive inverse, or is the additive inverse of itself. Now that's 2 out of 10 axioms. Still, we don't know that this is a vector space just because we checked 2. But these 2 are satisfied, and in particular, they're different than in C2. The 0 vector exists, but it's not 0, 0. It's 2, 2. Okay? And the additive inverse of every vector exists, but it's not minus x minus y, it's just xy. So let's check some more axioms. Okay, let's check commutativity. Commutativity says u plus v equals v plus u for every vector u and v in the vector space. In other words, we can change the order in which we add the vectors together and the result is the same. So let's see if we add xy and wz, if we get the same result if we change the order of the vectors. Let's see if this equation is true. Well, on the left-hand side, we have x minus w plus 2, y minus z plus 2. On the right-hand side, w minus x plus 2, z minus y plus 2. Notice the pattern here. We are using the definition of addition and the definition of equality, each in turn. All right, so so we've just used the definition of addition on both sides. Now we'll use the definition of equality and say that each entry in the vectors have to be the same. So the first entries have to be equal, and the second entries have to be equal. And we could quickly simplify this down, cancel 2's on both sides of both equations. We could add x to both sides of the first equation and add w to both sides of the first equation. It would simplify to this. Then we add z and y to both sides of the second equation. We get this. We get x equals w and y equals z. And this might be a little confusing because we're thinking, well, wait, what do we... This is the same thing that we got when we were solving for the additive inverse. So does that mean that this is true? Well, we wanted to check to see if this is true no matter what vectors we use. So no matter what numbers we plug in for x, y, w, and z, this always has to be true. And what we have just discovered is it will be true if x and w are the same and y and z are the same. Well, that just means if you've got the same vector and you're adding it to itself. So if we had, 3, 3, for example, plus 3, 3, well, that would be equal if we changed the order and put this vector first and then this vector second. Well, that's pretty obvious that they're going to be equal because we changed the order, but they're the same vector, so we didn't change the equation. Nothing really changed. Sure, that will always work. But if we have different vectors, if this is not satisfied, if this system of equations is not satisfied, then this vector equation is not satisfied. And so the commutativity axiom fails. It's not satisfied because this is not true for all vectors u and v in the vector space. It's only true for a very limited number of them, essentially if u and v are equal to each other. So the commutativity axiom is not satisfied, and that means that these four things, these two sets and the two definitions, do not form a vector space. And we checked 3 axioms, and we could stop right there. We don't have to check the other 7 because we found one that's not satisfied, and therefore we know the answer. This is not a vector space. If commutativity was satisfied, then in order to decide if this is a vector space, we'd have to keep going until either we found an axiom that was not satisfied or until we got through them all and we saw that they were all satisfied, and then we could conclude this is indeed a vector space. So that's how you check axioms. Don't assume anything. And in particular, don't assume what the zero vector is. Don't assume what the additive inverse is. You have to use the axioms to check them, which is also is the same thing as using these as the definitions to figure out what they are. In other words, we checked to see if the zero axiom was satisfied, and we discovered, in that process, we discovered what the zero vector is. If the zero axiom were not satisfied, there would be no zero vector. It wouldn't exist. Likewise, We used the additive inverse axiom, we checked it, and in that process we discovered what the additive inverse vector is. So don't assume what those things are, check them, and figure out what they are if they exist.